Okay, today we're going to talk a little bit about how molecules mix together. So we've been talking about the atom and the different parts of the atom, and then kind of what each of the different subatomic particles can do and the type of chemistry that it can do. And now we're going to talk about how these things mix together. So what we're really talking about is solutions. So in everyday speech we say things like, oh, the salt dissolved in the water. And what does that actually mean? Where does it go? What does it mean to dissolve? What it's actually forming is a solution. And we talked about solutions before. We said there's two types. There's the homogeneous and heterogeneous. And this is when we were talking about mixtures. So homogeneous mixtures, we said, are the same, right? So they look to the naked eye to be the same thing. You can't tell one pure substance from the other. And heterogeneous mixtures, which you can tell a difference physically between the two substances that are mixed together. So when we're talking about solutions and how molecules mix together in kind of a chemical sense, then we're talking about homogeneous mixtures or homogeneous mixtures, meaning that we can't tell the difference between one component and the other. And those components in a solution have specific names. There's two parts to a solution. You can have a solute, and the solute is the thing that you're dissolving into something else. So it's the thing being dissolved. And the solvent is the thing that you're dissolving into. Solvent. So the thing that is being dissolved, like salt, for instance, would be the solute, and the solvent would be your water. Okay, so these two parts make up a solution, and when we're talking about chemists and thinking about lab work, then solutions are incredibly important, and that's really what Chapter 7 is all about. So the solvent can be any phase of matter, but we usually think about them in terms of a liquid. And the solute can be any phase of matter. It can be a solid, liquid, or a gas, and we'll kind of talk about the different solutes and the different things that impact how well the solute dissolves in the solvent. So what we're talking about when we're talking about how well one thing dissolves in another, we're talking about the solubility. Solubility. And we know that there's some things that are more soluble in water, for instance, than others. So if you take table salt versus sugar, it's easier to dissolve table salt in regular water than it is sugar. And so we'll talk about the types of things that influence that solubility. Okay. So when we're talking about, and I've already been using the lingo, but just to round out our vocabulary, when we're talking about the one thing dissolving in another, that's the solute that is mixing into the solvent. So dissolving has a very specific chemical term and chemical meaning. So when we mix together the two parts of our solution, then we're dissolving them together. And only certain amounts of solute will fit in specific solvents. And so we can talk about the solubility limit of a solution. Okay, so it's the maximum amount of solute that you can fit in whatever the solvent is that we're talking about. So whether it's water or milk or hexane or benzene, whatever it is that we're trying to fit into that solvent, there's some sort of limit to it. So for instance, if I put 200 grams of just normal table sugar, which is called sucrose. If I have 200 grams in 100 milliliters of water, then this is the solubility limit of my sugar. Now this isn't something that you would be able to just pick out of the air. This is something that you'd have to do experiments in order to figure out. But this is my solubility limit. So at a given temperature, under given conditions, the maximum amount of my solute that I can fit in my solvent is my solubility limit. And if I have that 200 grams of sugar in 100 milliliters of water, then we say that that solution is saturated. Saturated. So saturated basically means full. It's as full of as much of the solute that it can fit in that given volume of solvent. Okay. So let's think about what would happen if I had less. If I put 150 grams of sugar in 100 milliliters of water, then now I'm below my solubility limit. So we say that the solution is unsaturated. Okay. Now let's think about another scenario. What if I heat up that water and I put more sugar in than my solubility limit? So if I put, let's say, 250 grams, so I have to change the conditions somehow, and I somehow pack 250 grams of sugar in my 100 mils of water, then now we call that a super saturated solution. So if you're at your solubility limit, we say that it's saturated. If you're below your solubility limit, we say that it's unsaturated. It is not full. And if it is greater than your solubility limit, and again, this takes some sort of outside influence, you have to do something extra to it in order to pack more of that solute in there, then we say that it's super saturated. So a super saturated solution. Okay. All right, so there's specific things that will impact a solute's ability to dissolve in a solvent, right? So we have a solubility limit, but if we change these conditions, like we talked about here with this last example, then we can increase how much of our solvent that we get into that given solvent, solute we get into that given solvent. So let's talk about those factors. One of them, and I already mentioned this, is temperature. If we're thinking about increasing the temperature of a solution, so let's say that we have a solution of a solid solute, like our sugar or like salt, in a liquid solvent. So we have a solid solute and a liquid solvent. If I increase the temperature of my liquid, what do you think is going to happen? Is that going to increase how much solid that I can dissolve or decrease? And hopefully you're thinking to yourself, well, I've seen this before. When I have boiling water and I put salt into my boiling water, then it dissolves quicker. Or think hot cocoa, for instance. If you have warm water, it's easier to mix your hot cocoa mix, or warm milk. It's easier to mix your hot cocoa mix in when it's warm than when it's cold. And so when you increase the temperature of that liquid, then you increase the solubility of your solid. Now we can also have different phases of matter for our solute. So let's consider for a second a gaseous solute in a liquid solvent. So that's maybe a little harder to visualize, a gas that's dissolved in a liquid, but it's really something that we interact with every day. If you think about soda pop, for instance, that's dissolved carbon dioxide in some sort of liquid gunk. Or I like sparkling water, for instance, so I have dissolved CO2 in my water, right? And that's a solution where the gas is the solute, the carbon dioxide, and the water is my solvent, okay? Now let's think about our raising the temperature. If I raise the temperature of my soda or of my sparkling water, so I open up the can and I leave it out on the counter, what happens to it? And you should be thinking, well, it goes flat. So what does it mean to go flat? When it goes flat, it's losing its gas. The gaseous solute that was dissolved in the solvent is no longer dissolved in there. So when you increase the temperature of your gas in your liquid solvent, that decreases the solubility. So we can think about that as it goes flat, right? That's the way that we talk about our sodas when they lose their fizziness, okay? Now another thing that impacts the solubility of both solids and gases is agitation or stirring. Because we're scientists, we always need to have a special term for things. So degree of agitation, which just really means stirring or shaking something. So let's think about this with our solid in a liquid. If I'm trying to get more solid to dissolve in a liquid, if I increase how much I'm shaking it up or agitating it, then what's that going to do to the solubility of my solid? Is more of it going to go into solution or less? And hopefully you're thinking more. Okay, because the more that you stir that thing up, the more that you agitate it, the more of that solid is going to be dissolved into the liquid. And now let's think about our gas. We've all experienced shaking up a gas that's in a soda pop, for instance. So we've shaken up a soda pop. So we shake up our can, and then we open it up, and we get bubbles galore, right? And the bubbles galore come from the gas leaving the solution, right? So the gas is now not dissolved into the liquid, and now it has no place to go, and as soon as you open up that gas can or that top of the soda pop, then it's going to all bubble out everywhere. So again, when you increase your agitation for a gas, that decreases how soluble the gas is in the liquid. So you can see that the two things that help solids, increasing the temperature and increasing the agitation, don't help our gases. And this is actually for similar reasons, and we'll kind of get into that a little bit later. Now there's one other thing that impacts gases and liquids, and this is pressure. Pressure actually impacts both solids and gases, as well as liquids, but it really has the most impact on gases. So if we have a gaseous solute in a liquid solvent, and I increase the pressure, so I'm talking about the pressure over the liquid. So let's picture the top of a 2-liter bottle here. So here at the top of my bottle, that's pretty good there. There's a cap. Okay, and the liquid in your bottle stops right about here. And if you looked at the top of your soda bottle, this just looks like empty space. And it's not the Coca-Cola company trying to cheat you out of those couple extra milliliters of soda. That extra empty space is actually pressurized CO2. And you know that it's pressurized CO2 because when you take that lid off, then it makes that great sound, that psh sound, right? Because all that pressurized gas is leaving. But while that pressurized gas is there, it is exerting force down on the liquid. Okay, so that pressurized CO2 is causing the gas particles that are dissolved in your soda to stay dissolved in your soda, which is why as soon as you open the top of this bottle, your soda starts to go flat. You start to lose some gas particles because you no longer have that bit of pressurized carbon dioxide helping to keep those gas particles into solution. So if you increase the pressure of a gas over a liquid, then that increases the solubility of that gas. Does that make sense? Okay. So these are just some factors that impact how well a solute dissolves in a given solvent. And what we're going to talk about in class and as we're moving forward in this chapter is really what the general rules are and what at a molecular level is occurring to cause these interactions. And the more favorable the interaction, the more homogeneous the mixture, and the better your solution. And we'll talk about those different features coming up in the next couple days. So if you have any questions, then don't hesitate to contact me, and I'll talk to you guys again soon.